Welcome to part 2 of this video series where we learn how to plot a three-dimensional spiral hose on Python. In part 1, we figured out how to draw the helical path that our hose is going to follow. In part 2, we're going to learn how to go forward from there. So, what we have so far is that we have this spiral path, and what we need to do on this part is we need to draw circles at various points around this spiral path. So let's take a closer look at one of these loops of our path. An interesting thing about this path is that we can draw numerous tangent vectors or normal vectors in this path. So first of all, we can draw a tangent at any point on this curve, and then we can draw a normal on this curve, and we can draw another vector that is perpendicular to both of these normal and tangent vectors. So this is our tangent vector, this is our normal vector, and finally this is our binormal vector. So the reason these vectors are important is that all of these circles actually lie on a plane that is created by the binormal and the tangent vector. So once we have these two vectors, we'll be able to draw all of these circles at the correct positions in their right orientations. So I'm gonna get rid of all of these things, and we'll start looking at how we can calculate those. So the first important thing is that the tangent vector that we need is simply equal to the Jacobian of our curve's function. So what is a Jacobian? Let's take a look at that. So a Jacobian of any function, say function f, and I'll write that in matrix form. Say we have r cosine of theta, and then r sine of theta, and m times z. So we have this function, which is basically a generic form of this function that we have right here. The Jacobian of that function would simply be the partial derivative of each of these elements on different rows with respect to different independent variable. So the first row would be the partial derivative of the row 1 with respect to r, the partial derivative of row 2 with respect to r, and the partial derivative of row 3 with respect to r. The second column would be the partial derivative of the first row with respect to theta. Same way, second row with respect to theta, and third row with respect to theta. And finally, our last column would be the partial derivative of the first row with respect to z, the partial derivative with respect to z for the second row, and partial derivative of the third row with respect to z. Now, if we were to look at our main function right here, we see that our only independent variable is t, or in this case, theta. So all of these rows can just be ignored. So our Jacobian in this particular case would simply be the partial derivatives of row 1 with respect to theta, row 2 with respect to theta, and row 3 with respect of theta. So what this means is, for now, our Jacobian of the function f is simply the partial derivative of the function f in terms of theta, or in our particular case, in terms of t. So let's take a look at how we can do this in Python. Now, what we have so far is that we made the spiral path. Now we'll take a look at how we'll calculate the Jacobian. Interestingly enough, there's two ways to do this in Python. First of all, I'll just go with the standard differentiation method, and after that I'll show you guys how to do it simply by using jacks. So in order to do it with differentiation, let's just make a generic function. So let's define a function called f that takes x as an input, and it returns, let's say, 3 times cosine of jnp dot cosine of 2 times np dot pi, just after that, 2 times x plus 3 times jnp dot sine of simply x. So we have that function that's being returned, just enclosed in brackets just in case. We have that. So let's make a function that actually differentiates this particular function. So let's define that as jc. This takes functions f as an input, and I'll create a closure here. So let's define another function, Jacobian, within this function, which takes x and dx as inputs. Now, another thing I also need to clarify here is that how differentiation is done. So basically, a derivative of any function, d with respect to t, is basically the function f. Let's call it x for now. The function of x plus dx, where dx is just a small increment in x, minus the function of x divided by the small change dx. So we basically also need to do this calculation in Python. And that's what we're going to do with this new function that we just created right here. So it would take x and dx as its inputs. So, and what do we want it to return? So okay, instead of doing that, let's say result of our differentiation is equal to the function of x plus dx minus the function of x, and all of it is divided by dx. So that's what we want this function to return. So let's have that as result. Just to make this more complex, let's say we want to do this for multiple arrays of values. So let's say we want to pass an array of x as let's say we want to pass x as an array such that the value here and here are different. So for cosine, they would use the value of the first element in the array of x, and for sine, we would use the second value in the array of x. Right. Again, we would also want our JAC function to return something as well. So let's say return Jacobian. Okay, now that we've turned the values of x as an array, we would also want, we would also get a result that is an array. So our result should, instead of being a value, we're going to turn that into an array. So what we would do here is we start the result as an empty array, and our calculation would basically append to that array. So we would also want to start a for loop here. So for I in range of x dot size, which means this is going to run for as many times as there are elements in the the list of x. Let's tap that, and what I'd also like to do here is turn the x plus dx into a variable. Let's call that xp. I'll start and define xp right here, which would basically be a copy of our list x, our array x. And here I would define our xp. The xp should get the value of x, our x, plus the small change dx. And in the end, we would also need to reset the value of xp. So basically what I do is this equals x of I. So all of this pretty much just takes a different, calculates differentiation of our function fx. So I would like to store this in a variable now, so let's call it jac equals jac of f. And there we go, we made our function. So let's try to calculate what the array would be, what the Jacobian would be for this function. So I will first pass two values for the values for x. So I want to send, what should I do? Let's just do 2 times np.pi. So the first value of x would be that, and the second value, let's make it 3 times np of pi. And once we get that, we also want to pass in the value of dx. So let's just make it 1e to the negative 6 for now. And let's see what value we get. So, okay, yeah, these are the values that we got, negative 5.9 and negative 3. So that's one way to do calculate the Jacobian. An easier method would be to just use JAX. So what I can do is I can use jax.jacobian, which is a built-in function inside JAX, and I want to calculate the Jacobian of our function f. And I'll store that in, let's say, jax, store that there, and I want to calculate jax again at these two values, 2 pi and 3 pi. So let's copy that and paste it here. This time we really don't need to supply a value of dx because that's just something that will be automatically calculated by JAX itself. So let's see what we get. And we get the same exact values that we got from our differentiation.